Okay, so let's get going with the afternoon session. Unlike a largish number of the talks up to now, the lectures, this one and the next one, will present a picture of the dynamics in glassy systems, looking at it from the point of view of kinetic constraints. What exactly that means, Rob Jack will tell us. And I want to thank Rob for coming here in the middle of various other constraints. And yeah.
Thanks for that sort of slightly enigmatic introduction. It's always good to have a bit of mystery about what's about to happen. So I've kind of split these lectures into two. The first one I'll talk about some models, sort of stochastic lattice models that it's easy to simulate on a computer and you can study analytically. And I'll talk about their properties and I'll try and motivate them as being glassy, if you like, as sharing features with molecular glass formers. And then in the second lecture, I'll try and go a stage further and talk about how various people, including Juan Garajan and David Chandler, have tried to build a real theory for glassy materials based on these models. So whatever you think about them as a theory for the glass transition, the models exist in the abstract, and we can study them. So that's what I want to do first, really, is talk about some properties that they have. So it's always good, I think, to start with an example. So what are kinetically constrained models? They're a family of models which are, in some sense, glassy. They have simple thermodynamic properties, so I'll explain a bit more what that means, but it basically means that they don't have any phase transitions in the conventional sense. You can usually write down their entropies as a function of temperature in some trivial way and just do calculations. And the motion in the system is constrained by their local environment. So you have in mind a crowded system in some sense. You know, if you're in the middle of a big crowd, your ability to move is basically constrained by the fact that there's people all around you, and it's hard to make any progress. And that's the kind of a picture that very many people have of a glassy material, is that basically it's very crowded and it's difficult for things to move. And we want to make some sort of explicative discussion of that fact. So it's kind of convenient that Julia already talked about case one this morning, or analogy of case one. So let's just think about an example of a KCM. So we'll think about particles distributed at random on a triangular lattice. So this is a triangular lattice with some round particles on it. And you just throw down the particles at random at some density. And in case one, so in a fairly trivial version of this model, you just say that particles, like this one, can hop to adjacent sites whenever there's a vacancy. So if there's a space, you can move into the vacancy and your old site becomes vacant. And for all particles, that happens with the same rate everywhere, which we may as well set to 1. And that's basically the lattice gas model that Julia put on the board earlier on, but now on a hexagonal lattice. And then we're going to do something slightly funky with it, slightly different, is we'll have what's called a kinetic constraint, which says that the particles live on the site, but we'll imagine that they're moving along the bonds. And we'll say that they can only move along the bonds, so from this site to this site, say, if there's no particles in the way. So this particle can't move to this site because this particle is clearly obstructing it. If I just try and move him along the bonds, he won't be able to make any progress. Okay? And then, well, I suppose you can take a particle out of the way, and then you would be able to move. So this particle can move in this configuration. In this configuration, I think nobody can move at all. And I wish this thing would go away. Good. So in a large system with density rho, you can prove that the model has an equilibrium steady state in which all possible configurations are equally like. That's for both case 1 and case 2. So case 1 is pretty much a trivial model. Case 2 is going to turn out to be a less trivial model. But for both cases, all configurations are equally likely in the steady state. Okay, so there's not much to say about it, apart from that this is an example of a model, and you can imagine that it's easy to put it onto a computer and just run a computer simulation and see what happens to the particles. And you might imagine that because of when you do the case with a constraint, the particles tend to move slowly because everyone tends to be getting in everybody's way. And so here's a simulation. So it's easy. You can measure any. No, you can't measure any observable that you would measure for a glassy liquid, but you can measure most of them. And in particular, you can measure the self-intermediate scattering function at any wave vector you like. So I just choose some large wave vector, and I measure it as a function of time on a log scale. This is time going this way. I guess the axis disappeared. Time going this way, self-intermediate scattering function going this way, And the different curves are increasing density. So density is the only parameter of the model now. And as I increase the density towards 1, so I guess this is about 20% density, and this is probably about 80% density. As you increase the density, the relaxation time increases from a number which is basically 1 to a number which is somewhere around 10 to the 7. So you've got a large change in relaxation time with a changing structural parameter. And that might remind you of some kind of colloidal system or some kind of granular packing. So basically the only physics that we've put in, the only thing that we've put in at all is crowding, basically. And we've managed to arrive at some rapidly increasing length scale. And you can see that this correlation function has some complicated shape. I mean, it's not just a simple exponential here. So there's something which, there's no plateau because there's no elasticity in the model. But there's something happens up here, and then something else happens down here. So there's, in some sense, two-stage relaxation in this model. Okay, so that's just an example. So it's an example, and the point is that the kinetic constraint was you can only move if there's nobody obstructing the bond you're moving along. So what are the key messages from the example? It's easy to define these things. It's easy to simulate them. It's even possible to study them. I haven't really said the how. I'll just state this as a fact for now. They can exhibit complex behavior, including large relaxation times I showed you, slowing down of the diffusion of single particles, lots of dynamical heterogeneity, intermittent motion, increasing chi4, all that menagerie of things that we've come to associate with glasses. But there's some things that they don't have at all. They don't have entropy crises, because I told you that the entropy is a simple function. They don't have glass transitions in mode coupling theory or in the sense of Kautzmann transitions, so no TK, no T0, no T0 fit, no TC, nothing like that. They don't have any elasticity. So I've put these particles on a lattice now, and it's clear that I've thrown something away when I do that. So all that sort of wobbly elastic motion that you can think of in a real liquid, I don't have anymore. And we can wonder about how much that's going to hurt us later on. And I just want to put this advert up here, right? So if you really want to know about KCMs, you don't even have to come here and listen to me. You can read this great review from 2003. It's about, I don't remember, not quite 100 pages long. It has a lot of important information in it. And for any details, that's where I would refer to anything pre-2003. So we have done some things since then. By simulation. So I don't know a way to do an analytic calculation of that. So it's a computer simulation, absolutely, by these guys. So I haven't put any proper references in here. I've got a list of all the things that I've referenced, and I'll post it on the web or something if anybody wants the list. Okay, so now we have to go back and think in a more general way about what a kinetically constrained model is. So I just gave you an example, but what in general do we do? So you take a lattice, so for example square, it has sites, n of them. And let's just for now imagine that we have binary variables on every site. So every site is either in state 0 or state 1. So you just tile a lattice with 0s and 1s. And then let's just think about a model without any kinetic constraints. So you just have two dynamical rules. You say, if I'm in state 0, I go to state 1 with rate c. If I'm in state 1, I go to state 0 with rate 1 minus c. And that's a completely trivial model. You can imagine simulating on a computer, but you don't have to, because you can solve everything with a bit of paper on 1 minute. So all the spins are completely independent. There's no coupling between the spins. What they do just depends on their state. And in the equilibrium state, the probability that any spin is up turns out to be c with these rules. So the mean density is c. So this says the average value of ni. The mean number of up spins is c. And for any pair, they're independent. So the probability of having two separate sites, both in state 1, is just c squared. Okay? So these properties are trivial, but not only are these properties trivial. Oh well, we can keep going. So you can define the energy of the system to be the sum over all sites of ni, so that just says count the number of upspins. And if you do that, then the temperature naturally comes out to be related to c in this way. So exponential of 1 over t is minus 1 over t is c over 1 minus c. So that's just, you just crank the handle. It's trivial to prove all this stuff. And you can calculate dynamical quantities as well. So the probability that any spin is up at both of 2 times t and t prime in equilibrium can be calculated, I said. It's given by this angle bracket here, and I'm going to define the correlation function to be this connected correlation function, which I can calculate and show it has this form. That's what this is, the correlation function at equilibrium. And it's also useful to find the persistence function, because that turns out often to be easier to work with. So the persistence function is the probability that a particular spin does not flip at all between 2 times t and t prime, and it takes this form in this model. So it's just basically a simple or sum of two simple exponentials. This one's one single exponential. So there's absolutely nothing happening here. I've just got spins. They flip up and down at random independently of each other with some rates. So then, what's a kinetic constraint in this context? So one can go back to the paper of Fredrickson and Anderson, which is one of the early papers on kinetic constraint models. They're FA. They're going to be called F and A throughout. So lattice in d dimensions. Okay, and then you say, I'll have the same rules as before, but the only spins that are allowed to flip are the ones in which at least f of their neighbors are up. Okay, so you have a spin, and he's in state 0 or 1, and he has some neighbors, and they're all in state 0 or 1 as well. And you say, well, I'm not allowed to move unless at least f of my neighbors are in state 1. Is that clear? It's clear that I can make this rule if I want. Yes? It's clear that I can. So here's an example. Okay, if the spin flips. So here's an example. So I just imagine one dimension, put some spins on a line, 1, 0, 1, 1, 1, 1, right? So this is red one and this red one. I don't know if you can see the colors, but these ones don't have any up neighbors, any neighbors in state 1, so they can't flip. Okay, but all the others can flip, and they flip with rates c or 1 minus c, depending on whether they're up or down. And you note from this rule that if the transition from state A to state B is allowed, so is the transition from state B to state A, and that's going to turn out to be important. So for example, if you flip this spin, which you can flip because he's got an up neighbor, he becomes 1, and you can always flip him straight back again because he's still got an up neighbor after the transition. Okay, so if you don't like these definitions in terms of rates, here's an operational definition of the model. Here's how you would do a simulation. You take a lattice, it's in some configuration. You pick a spin at random, so pick a site at random. If it's down and it's allowed to flip, I change it to up with probability c. If it's up and it's allowed to flip, I change it to down with probability 1 minus c. Otherwise, I do nothing. Repeat n times. That's one time step. Everything is easy, right? Is there anything there? No. And the final thing that I should say, which I don't know if everybody knows or not, so if A and B are states, and there exists a probability function P of A, such that for all pairs of states, this condition is true, so W is the rate of going from A to B. If there exists a function P that satisfies this for all states, then it turns out that P is the steady state of the model. So that's sort of standard stochastic model analysis. I don't propose to prove it, but it's really very easy to prove if I was going to prove it. And for all these FA models that I've defined, and for the trivial model that I defined at the beginning, I know this function, and it's just equal to the number of upspins. It's equal to c to the power of the number of upspins times 1 minus c to the power of the number of downspins. So I know the probability distribution, the probability of any configuration in the steady state for this whole family of models described by the dimension d and the value of this parameter f. Okay? And the key point is that when I introduce the kinetic constraint, I set some of these w's to 0, but I always set the reverse one to 0 at the same time. So I don't do anything with this condition. And so the probabilities of all configurations at equilibrium are unchanged when I change the constraint. And what that means is that these equations that I derived before, like the probability that a spin is up or the probability that a pair of spins is up, just has the same formula regardless of the constraint. But the dynamical properties of these systems are going to turn out to be very different, because the spins are not independent anymore, because the constraint tells you that what happens to this spin depends on what happens to its neighbors and so on. So the correlation function, the persistence function, which I gave you analytic formulae for before, I can't give you analytic formulae anymore, but they're going to be different, and they're going to depend on the constraint. And the difference between the models are going to be most significant when c is small, because c is the average number of upspins, and you have to have upspins around in order for things to happen. In order for motion to take place, you need a few friendly upspins to help you out. And that's going to be rare at low temperatures, so the dynamics are going to be slow. And that's where the interesting behavior is going to occur. It's okay? So here's an example. So here's an example which hopefully will illustrate what I'm talking about. So I'm just going to take the FA model in dimension 1, and I'm going to let S should be F here. So F is F. It tells you that you're allowed to flip if you've got at least one up neighbor. And what I've got on the left is a picture of a trajectory in the model with no kinetic constraint. So what I've done is I've taken all the black spins at time 0, and I've colored them black on this axis. This axis is a spatial axis. And I've just drawn a black spot wherever there are up spins. And then I've done the same for time 1, and the same for time 2, and the same for time 3. And I've put them all next to each other, so it looks like a comic strip, right? Or like a movie. Time goes this way, space goes this way, and these are the positions in space and time of all the up spins. And it looks like a mess. It looks like a snowstorm, because there's no constraint here. There's nothing happening to create any correlations in the model. And in the right-hand picture, I've shown the FA model, and you can see that what's happening now is that the mobile sites, the black sites, are following each other around, making these lines that appear in space and time. So these are typical trajectories of the system. Now, a configuration of the system is just the positions of all the black blobs at equal times. And statistically, that's the same from the left and the right-hand side. That's the point of these models, right? Is that statistically speaking, the vertical lines always look the same. And so there can't be anything going on with the entropy. There can't be anything going on with correlations between these black things in space alone. And if I changed it to be f equals 2, or some higher dimension, and I changed f still further, I would see different things again. So always what I see depends on the rules, which is not so surprising if you like. Maybe what is surprising is that you can change the rules while keeping the distribution at constant time constant. Okay, so then it becomes a bit of a zoo, right? You can write down any rules you like, and you'll see some interesting behavior, maybe, or maybe you'll see some not interesting behavior. I mean, who knows? So here's some notable examples which I will come back to, so that's why I put them up. So the east model in one dimension, it's called the east model because spins may flip only if their left neighbor is up. So if I'm a guy and I'm up, I look to my right, and I say, well, now you can be up as well if you want. You're allowed to change now, but the guy on my left isn't allowed to change. So that's why it's called east, because you look to your right. It could be called the right model, but it's called the east model. And that has different behavior to the FA model, which says that if I'm up, I'm allowed to flip the guy to my left or the guy to my right. So what happens does depend on the rules. And another thing that I could do, along the spirit of the TLG at the beginning, is to consider this model due to Cobb-Anderson, where you have particles now. So instead of having spins that can be up or down, I have sites that can have a particle or no particle. And I say a particle may move to an adjacent vacant site if it has at least S vacant adjacent sites in both the initial and final states. So that's just a rule. I can obviously write it down. I can obviously put it in a simulation. It's not obvious that I can do any theory with it, but under some circumstances, I'm stating that I can. And it turns out that this Cobb-Anderson is related to a related FA model, but FA is Fredrickson-Anderson. KA is going to be Cobb-Anderson. Okay, and I can also define the stupid model, which says particles on a square lattice may never move. And that's in the spirit of all the other models, right? It's a constraint, a kinetic constraint that's pretty idiotic. But the point is that we need some restrictions on what kind of constraints we're going to use in these models. Otherwise, we're just looking around in the dark. And there are two important questions which we need to think about. The first one is, if I take a typical configuration of the model, are the spins that I know for sure in that configuration will never be able to flip? And that's related to what's called the reducibility of the Markov model. So you can imagine that, well, in the stupid model, no spins can ever flip. So all spins have this property. And then a second question is, does the system explore its configuration space in some finite time? And that's well known, I guess, to people who've been thinking about the glass transition as a question related to ergodicity. And then you can ask other questions like, for particle models, is the diffusion constant finite, for example? And it turns out that if you just write down some set of rules and try and answer these questions, you may have a hard time of it. It's not an easy calculation to do for most of them. So let's just give an example of a situation in which one might do such a calculation. So an irreducible system is one for which, for any pair of states, there's a sequence of possible moves that turns A into B. So that's a condition that I can think about for my model. So for example, if I have this rule that I had before that I can only flip if I've got at least one friend who's up, then if I put all the spins down, nobody can flip at any time forever from that configuration. So I can't reach any other configurations from that configuration. And in particular, I can't reach the all-up configuration, just for an example. So that means that the system is reducible. But so that might mean that this would be a bit of a strange model, but in fact it's all right, because apart from that state that's all down, where everybody's a 0, all states are connected together. So I've got 2 to the n states in my model, and 2 to the n minus one of them are all connected together. So I can consider those as forming a sensible model because, and for a large system, I basically never encounter the all down state, so I don't have a problem. Okay, that's the simplest one for FA with f greater than 1, and for all the other models, there are lots of states that can't be transformed, typically. So if you pick a pair of states, it's not guaranteed you can transform between them. But the system is effectively irreducible if this constraint is true. And that was proven in the original paper by FA. Basically, it says that if you take two equilibrium configurations, then it's almost certain that you can get from one to the other by some sequence of moves. I'm going to say something about that in a minute. So if you're in the mathematics world, then I think they think that wholesome models should be irreducible. But you might not insist on it completely generally. In models that spontaneously have phase transitions, then they would be irreducible. Because there always exists a route from all up to all down, even if it requires you to go over an infinite barrier. So the Ising model is irreducible because you can always go from all up to all down. Just flip the spins one at a time. It might cost you a lot of energy, but you can always do it. So here's a nice example of a reducible system. You just put two disks in a box, and they're hard, so they can't go through each other. You put the linear size here to be L, and then you decrease the linear size until such a stage where they can't pass each other anymore. So this system is irreducible because it has all states are reachable from all other states. This system is reducible because this state can't reach the one where B and A are the other way around. And this is supposed to be an argument somehow for how reducibility is related to the physics of the glass transition, right? Crowding, particles not being able to pass each other, all those kinds of ideas are sort of familiar from the world of the glass transition, right? At least in the world of the glass. Sorry.
No, but isn't this something that will strictly only work when you have hard particles?
Yes. So it is an artifact of hard particles. Hopefully it says somewhere here that there are hard particles. No, it doesn't. They're hard. They said they're hard. Good. So yes.
This distinction.
Yes.
This concept will be used only when you have hard constraints.
Yes. So the natural way to do it would be to say, well, I can violate my constraint with some small rate epsilon, and then I'll let epsilon be very small. But my point is that if you're going to use hard constraints, if you're going to deal with hard particles, then you have to think carefully about reducibility before you start. Otherwise, you might just end up with nonsense. So I'm not really going to address the question of ergodicity, except to say that sometimes even ergodicity can be proven. But I'm really only talking about reducibility here. Okay, so yes, that's I guess what I wanted to say. I guess that's clear, right? Reasonably. So then there was a question about what I'm going to insist on for my models. So I'm thinking about modeling. In the end, I'm thinking about modeling a fluid, and I know about fluids at high temperature and low density. I'm going to insist that my fluid behaves as a simple fluid at high density. So I'm going to insist on effective irreducibility and ergodicity with finite diffusion constant at high temperatures and low densities. That seems pretty reasonable to me. And then I can ask what happens when I start changing those parameters. And the models that I've introduced all have this property. So the East model, the FA model with F less than or equal to D, the K model, this one, the TLJ model that I introduced at the beginning, they all have this property. And it turns out that they're all ergodic and effectively reducible at all temperatures and densities, in fact. So that's not true for all models, but it's true for these models. Okay, so what did I want to say about this? So why were these models introduced in the first place? Actually, they were introduced by people who were interested in mode coupling theory, and they wanted models that they could play with and prove something for. And so they wrote down these models and said, well, we don't know what's going to happen. And they did mode coupling theory on it, and they found transitions at finite density all the time. And I don't know what they thought when they found that. But then later they proved that the transitions were artifacts. So I'm not saying anything about MCT when I say this, but I'm just saying that it's useful sometimes to have a model that you can actually prove something for. So just because there's no MCT transition in these models doesn't mean there's no MCT transition in any other model. But it's useful to have a specific system where you can do a specific computation and try and prove something. And that's really the spirit of what I'm going to say here, is that these are models where you can ask all the questions that you're asking about your liquids, and you get a simpler answer usually. And it might be that you get an oversimplified answer, but at least you get an answer that you can understand. So for these systems, the reason there's no transition is an answer we can understand. You just go and read Giulio's paper with Christina, and you'll be fine. Okay, so these things are ergodic disordered states. So they don't have any sort of particular clustering of the particles or any microstructure or anything strange like that. So it's kind of natural to think about them as fluids, if you like. I mean, they're obviously not crystals or gases. I haven't really shown this, but well, I've shown that the relaxation is slow. I haven't really shown that it's cooperative and heterogeneous at high density and low temperature, but it is. So I'm going to say that in a minute. So if they're fluids, they're kind of glassy fluids, really. And so there are kind of two classes of question that we could ask. We could ask, if we write down a model with some rules, can we explain what we observe when we make a measurement on that model? And then there's the second question, which is perhaps more deep or more difficult or more speculative, which is, if I study these models and I find a bunch of mechanisms and phenomena for producing dynamical heterogeneity and all those things, does that have anything to do with what's happening in the real world of liquids? So those are, if you like, two classes of question. And I guess I'm restricting myself for the moment to this class, although perhaps I'll say a little bit about this class later in this lecture or in the next lecture. And of course, the answers always depend on the model, right? And it's fortunate that the answers depend on the model, really. So I've been banging on about how these models show cooperative and interesting and complicated dynamics. So I thought I'd just show you a picture. So dynamical heterogeneity you've heard about from Ludovic Berthier and maybe from lots of other people. And basically, well, I think it's the idea that different regions of a liquid are faster, slower than average if you look at a given time. And it's a very strong effect in kinetically constrained models. Some people would argue that it's too strong in kinetically constrained models for them to be realistic. But it's certainly a strong effect. We can see a strong picture of what's going on. So this is a TLG model I introduced at the beginning at some finite density. And this is 4 pictures at different times. So first time, second time, third time, fourth time. And colored black are all the particles that have moved at least once between time 0 and the time when I make the measurement. So if you make a measurement at an early time, you see kind of spotty features where all the black guys are kind of clustered together here and here and here and here. And there's some background of guys who have never moved. And gradually what happens is that the places where motion has happened spread out into these patches. And then the patches merge. And then you're with a picture which is nearly all black. So nearly everybody's moved apart from a few pale patches at the end. So if you try and make this kind of picture for a 3-dimensional glass-forming liquid, you won't get anything as striking as this. So part of the reason it's so striking is that I know when a particle's moved now for real. So if a particle moves, they move in a discrete jump, something happens, I can see it, I can color it a different color. Okay, why am I showing this? Well, once you've got these pictures, I think it's quite natural to know what to do next, which is that you take the correlation function of the black particles and try and extract a length scale and a susceptibility from this kind of picture. And that's what chi4 is, and that's what G4 is, these length scales and time scales that we've been hearing about. Okay, so this is the 4-point function in this model. I'm just going to take, so P is 1 for the gray guys and 0 for the ones colored black. This is the 4-point function, so it's just the correlation function of this field. It decays to 0 as you go far apart on a characteristic length scale, which is what has been defined as psi4. And we also have chi4, which is basically the sum overall space of this thing, which somehow measures the weight of these clusters in some vague sense. So these don't come out terribly well. On the right, there's a plot of, this is basically chi4 for a version of the East model. It's not so important anyway. What's really important is the shape. So you can see that chi4 as a function of time for any given temperature has a peak and then decays to 0, and the height of the peak and the time at which it's maximal is increasing as the temperature is reduced towards the glass transition in this model. So one can measure chi4. It has the same typical shape as it would in a glass-forming liquid. And you can also measure an increasing length scale fairly accurately in these models. So the broad features are basically similar, but both between these different models and between these models and glasses. So one thing we'd like to know is, based on the microscopic physics, can we tell how this length scale or this length scale depends on the temperature and the density in the model? Can we explain the scaling of these quantities and why they increase as we approach the glass transition? So a particular easy example is to go back to this FA model in D equals 1 with F equals 1. Spins may flip if at least one neighbor is flip. Spins may flip if at least one neighbor is up. So here's an example. You start with 0, 1, 0. So either of these zeros can flip because they've got an up neighbor. So let's suppose this one flips. Then the original one can flip down because he's now got an up neighbor. And what I've achieved is diffusion. So this particle has moved to here. And by a similar sequence of moves, you can achieve branching. So one particle can go to two particles. And by running it backwards, I can achieve coagulation. So I get from two. So I'm calling them particles, but I mean excitations. I mean upspins. So I've got these upspins, these ones. I can have them branch into two. I can have them diffuse, and I can have them coagulate. So loosely speaking, if I'm thinking in periodic boundaries, I can have space as a kind of circular axis, and I can plot the positions of these upspins, and they tend to diffuse around and coagulate and branch. And the rate for the diffusive steps turns out to be proportional to the parameter c. The distance between them is 1 over c, because the probability of having an up one is c. And so you can estimate the time at which they meet, which is tau is the length squared divided by the time, and that's 1 over c cubed. And then if you measure the relaxation time of this model, then you'll find that this gives you the right relaxation time. So that's how, it turns out for this simple model, just simple scaling arguments like this tell us how big the relaxation time is and how fast it grows as I go towards the glass transition. That's basically the same, except that I've noted here that c, I said before, scales as exponential of minus 1 over t. So this basically gives me strong glass form of behavior. It gives me simple activated scaling at low temperatures. And you get scaling forms for the correlation function as in critical phenomena. So there's really a good scaling limit that's well behaved for this model as the temperature gets small, where you have an increasing length scale and an increasing time scale. And this is the kind of, well, one idea for a mechanism for getting glassy physics basically is that you have a time scale and a length scale growing together. And here they're growing as a power law. So the time is growing as c to the minus 3, the length is growing as c to the minus 1. Okay, I put some notes on dimension greater than 1, but I'm not going to bother with it, I don't think. Oh, maybe I'll just say the last point. So in all dimensions, it turns out that you can work out how the 4-point susceptibility depends on time, and it increases with this t to the half law before the peak. And that doesn't fit data from liquids, but that's really a question for tomorrow. But the point is that we can say how chi4 will increase as time goes by. So it's just simple scaling arguments all the time. We can work out things about these models. Okay, so for the yeast model, you can do a similar argument, and the answer, I suppose, is sufficiently interesting to go through. So let's suppose we start with this state 1, 0, 0, 0, 1. Then I can flip this guy here because his left neighbor is up. But then I can't flip this guy now because I can only flip if my left neighbor is up. So the only guy who's free to flip now is this guy and this guy. Most likely, I just go straight back. Most likely, this one goes down before the next one goes up, because the up rate is much smaller than the down rate in the interesting regime. But I can make this pathway of flips, and in the end, it allows me to flip this one here to down. So this one started off up. He's up in all these configurations until I get to the last one when I've been allowed to flip him down again. And it turns out that the important question for this model, so this is just some particular rule, the important question is, when I have two spins a distance L apart, how long does it take before I can move the right one? And that's a question that you can answer by a scaling argument, and it turns out to go like in this rather strange way. So it goes as c to the power the log of the distance between the upspins. And since the typical spacing I know from just the thermodynamic properties of the model, I can derive the scaling of the relaxation time, and it's not strong glass style anymore. It's become what's called fragile superheterogeneous. Specifically, this exponential of 1 over t squared is called a Bessler form, but that's really a detail. So two things to notice. The relaxation time is increasing in a fragile way with the temperature, and the length scale and the time scale are not related by a power law anymore. The time scale is depending in some complicated fashion on the length scale. And so I don't really have a good analogy with critical phenomena anymore, but I still have this sort of typical property of increasing length and time scales in the model. And this is similar in all dimensions for East-like models, at least if you generalize them appropriately to higher dimensions. Okay. This one? This one here. Oh, this one? So it takes a moment. So the typical length, the typical distance between excitations is 1 over c. And 1 over c is e to the 1 over temperature by definition of, by the relation between c and temperature. So c is always e to the minus 1 over temperature, approximately, for low temperatures on low c. And then I have that psi is approximately 1 over c. And what I want actually is the log of the length scale. So log of psi is approximately 1 over t. And then I want c to the power log of psi there's a minus sign missing somewhere, but it's close. C to the log psi, so log psi is 1 over t. So this is c to the 1 over t, which is e to the 1 over minus 1 over t to the 1 over t, which is e to the minus 1 over t squared. So there should have been a minus sign here. And I would have it right. So, okay, so again, so c is the number of upspins on average in the model. And that's a number which is depending on an Arrhenius fashion on the temperature. And so the typical distance between upspins in one dimension is just 1 over c. In higher dimensions, it would be 1 over c to the 1 over d. So then I can take this log and then plug it back into this expression here with a corrected minus sign in front. And that gives me this fragile behavior. So now you're going to ask me how to get this logarithmic dependence. And you have to do that by sort of doubling the distance between them each time. So you can prove that if you double the distance between them, there's one more power in this expression. Basically, you have to have in mind that, well, you have in mind that the time to do something is governed by the largest energy barrier on the route between the two states. And you can calculate the height of the largest energy barrier in this model at low temperatures. So why am I going through this? I guess I'm going through it because I think it's important. It focuses the mind on questions like, when is the relaxation time governed by the largest energy barrier in the system, and can we estimate that largest energy barrier? Or when is it governed by sort of diffusive motion as it was in the one-spin facilitated FA model? So this model is different from the previous one because this model, I said the physics is basically that of diffusion. And here I'm saying I've got the physics of the largest energy barrier between two states. And so there's kind of different mechanism for increasing timescales in these models. I'll only say 2 words about the cooperative models. So FA models with higher values of f are more difficult to do any sort of real analysis of. If you do quite a lot of work, you can prove that the relaxation time is bounded by the exponential of 1 over t. And for temperatures getting small, that's a very, very large number. So large, in fact, that it becomes extremely difficult to simulate these things or even to test this scaling behavior, which is perhaps unfortunate, but I think we can assume it's right. So it's... Do I want to say anything about how you prove this? I don't think so. You have to consider on how big a length scale you have to make changes to the system in order to get from configuration A to configuration B, or in order to move any particles. Okay, maybe this is useful actually. So I said that when you're considering these questions of reducibility, it's useful to invoke a large system. So if you take a small system, even for the simplest model, there's a sizable probability of finding all the spins down, and then nobody can move at all, and you can't forget about the fact in that situation that the system is reducible. So there's always a length scale at which the system crosses over, and you start to notice that it's irreducible after all. And that length scale is sometimes called the bootstrap length because of the way that you derive it by what's called bootstrap percolation, and it's the smallest system size for which typical configurations can now start to notice each other. So the smallest system size for which the system can relax. And in that sense, it has a little bit of the flavor of a pointer set length in the sense that once you start considering small systems, it gets harder and harder to relax. But it's actually quite different to a pointer set for a reason which I may discuss at the end. And this seems to be the interesting length scale. This big size seems to be the interesting length scale that replaces this simple length scale, which was just the distance between defects. And this is the length scale that you now have to start using in your scaling arguments. But you can always do that. You can always do that, even if you can't measure this thing easily. And if this length scale diverges, which it may do at some temperature or density, that would be an ideal glass transition in which the system would become non-ergodic. So correlation functions would no longer decay to zero. And I guess in answer to Sri's question before, partly, if you then soften the constraint, correlation functions would decay to zero. So this feature is really a feature of the hard constraints in the system. But it would take a very long time. If the constraints were fairly hard, it would take a very long time for it to restore ergodicity. And in fact, we don't make experiments over infinite timescales. We make simulations over practical and experiments over practical timescales. So there are models for which this is known to occur. For example, the North and East model and the Knights and spiral models of Christina and Giulio and Daniel Fisher. Yes. Okay. So, right. So what I've I guess tried to persuade you is that you can always write down these models, and you can always simulate them, and sometimes you can analyze the scaling in them. But I guess the thing that I wanted to emphasize most of all is this quality of heterogeneous dynamics and measurements of dynamic susceptibilities and length scales and things like that. So it's this length scale here that we'd really like to know for the liquid. We'd like to know how this length scale depends on temperature and on the method you measure it. So we'd like to know that kind of quantity. And these are the kind of things that we can estimate by scaling arguments in kinetically constrained models. So they're a kind of tractable set of model systems where you can really do the calculation that you'd like to do for the liquid, both numerically and with scaling arguments. So that's the reason that I went through some of these scaling arguments was really just to convince you that they can be done. So in the spirit of what we said this morning, I just wanted to say a few words about how kinetically constrained models can be realistic, given that we don't have hard particles and hard constraints in the real world. And one way to do that, not the only way, but one way to do that is to think about these things that I call plaquette models. So now you have to get your head around I wasn't going to talk about this, but after this morning's discussion I thought I would. The reason I wasn't going to talk about it is that now you have to get your head around different models again. And I apologize for that, but that's just life, I'm afraid. So now I'm thinking about either a square lattice or triangular lattice. And on the vertices, I'm going to put spin sigma, and sigma can be plus or minus 1. So then I could have the Ising model if I just said that the energy of the system is given by the sum over all bonds of sigma I, sigma j along the bond. Right? That would be the Ising model. Everyone's happy, more or less, I hope. So instead of doing that, instead of making a sum over bonds, I'm going to make a sum over square plaquettes of the lattice. So there's a site here, a site here, a site here, and a site here. I'm going to take the product of the four numbers, the four spins, sigma, which are plus or minus 1, and I'm going to make a Hamiltonian, an energy function, out of the product of those four things. So this product is plus or minus 1, so this is a sum over n terms, all of which are plus or minus 1. And I can do the same on a triangular lattice, where I take the product of 3 spins around each individual fundamental triangle. And then I just imagine it was an Ising model, but now I've got more complicated interactions. And I flip the spins with metropolis rates, so I calculate the change in energy on flipping a spin, which I can do from these expressions. And then I just accept or reject with a standard metropolis probability. So probably everybody knows what metropolis probability is, right? At least some people do. So at first sight, this just looks very complicated. It's not obvious why you would write this down, and it's not obvious to suppose that you could prove anything. But it turns out that these are actually simpler than the Ising model in some important respects, which is that you can calculate the free energy of these models at all temperatures by a sort of simple mapping. And it turns out they have the same free energies as kinetically constrained models. So I'm not going to explain the proof, really, except to notice that this product here is another Ising-like variable. So this thing can also be equal to plus or minus 1, so it's like a new degree of freedom. You could call it Tor. And it turns out that once you make that duality mapping, then you can analyze the models a bit in some complicated way. But what's important here? Okay, what's important here is that suppose I flip this spin. Then this goes from being a plus 1 to a minus 1, and that means that the 4 spins around this square, their product changes sign. Okay, so if I've got sigma 1, sigma 2, sigma 3, sigma 4, and I change sigma 1, I change the sign of sigma 1 to minus sigma 1, then this thing goes to minus its original value. And that's the same is true for these 4 plaquettes here, all of them. And so you can imagine 4 situations. So the simplest situation is when these products are, well, I could have had a minus sign here. These products are all plus 1, let's say. If I flip the spin in the middle, they would all be minus 1. And that would cost me either cost me an energy of 4 units, or I would get back an energy of 4 units, depending on what the sign is here. So sometimes when I flip a spin, it costs me energy 8 units, 4 units. Sometimes when I flip a spin, the energy cost is 4, let's call it 4j. And so this thing happens with a small probability if j is a large number. So this is the rate for flipping a spin that's for which the 4 plaquettes are all in a particular state. Okay, but there are other ones that flip with rate e to the minus 2j, and there are yet other spins that flip with rate 1. So now I can say, what happens if I never allow these processes to occur? Because they're the largest energy barrier in the problem. So let's just suppose that they're not allowed to happen at all, instead of happening with a very small probability. What does that change of the physics? Well, at low temperatures, it changes nothing at all, because it's the biggest energy barrier. So as I lower the temperature, I can either let these things happen with a small probability, or I can just forget about them completely. And I can prove that nothing changes. At least I can verify by numerics that nothing changes. And the reason to mention this is it's an example of how an effective kinetic constraint arises from some hopefully not too stupid looking dynamical rules. So these just look like spin models. You wouldn't know that these were kinetically constrained models if I hadn't told you. But it turns out they behave like kinetically constrained models. And basically they behave differently, but so far everything I've told you is the same for both of them. So they both behave like kinetically constrained models at low temperatures, based on this Hamiltonian. So this is a sum over squares, the products. This is a sum over downward triangles, the products. Okay, so what can one prove for these models? Well, the first thing that you can prove is that the relaxation time of the square one, so SPM is square plaquette model, so the square one, the relaxation time scales as e to the 3 over t, which by coincidence is the same as the FA model I said before, but the thing to notice is it's Arrhenius or strong glass, and the triangular one has 1 over t squared, which is sort of Bessler-like. So you can get, quotes, strong and fragile behavior, regardless of whether you interpret anything by it. The second thing that you can do with them is calculate point-to-set lengths, and dynamical heterogeneity lengths, and dynamic point-to-set lengths, all in the spirit of the discussion this morning. So this is a way to really make concrete the things that you're thinking about these length scales, and whether they can be the same or whether they can be different. So really, I don't really care what the answer turns out to be, for the specific length scales, but I'm interested in whether they always follow each other or whether they can decouple. So what's true? So the dynamic correlation length one can easily infer or measure, and it turns out to be the same as dynamic point to set for both these models. So you'll remember that point to set is the thing where you freeze the boundary of a cavity and let dynamics happen within the cavity and ask how long it takes for relaxation to occur and how big the cavity has to be before you recover the bulk behavior. So these length scales are the same. Okay, I wrote this and then I wasn't sure if I agreed with it, but it's definitely true that you can define a length scale by asking at what point does my cavity start to have more entropy than 1? And what I'm going to say is that nearly all the relevant states here are minima of the free energy, a minima of the energy. So I'm just going to say that the entropy is the same as the configurational entropy, which is a bit dodgy. But if you interpret configuration entropy as just the number of minima of the energy, then it's fine. And then this is true. Okay. I think I've got another bit here. Okay, no, I haven't. But the static and dynamic point to set lengths, I put it up here, are different in the square model, although they're the same in the triangular model. So if you remember, these were Giulio's 3 things to test, whether they're all the same this morning. And the first point is that you can test them. The second point is that for the triangular model, it seems to pass all the tests, which is kind of surprising, given that it's such a simple model, if you like. Now, you can argue about this one, but I think it does pass these 2. And certainly it doesn't pass them all in detail, so it doesn't pass, well, never mind, we can discuss. So RFOT, naive RFOT, I think, predicts that all the 3 length scales are static. Static point to set, dynamic point to set, and dynamic correlation lengths should all be the same. That's the naive. Is that right, Julio? That's the naive prediction? So I thought that the naive prediction... It's all right, you weren't snoring. The naive prediction is that the psi4 and the 2 point to set, static and dynamic, should be similar in RFOT. Naively. So okay. So I was claiming to 3 that maybe it's a bit surprising that seems to be true for the triangular model for some definition of configurational entropy. It's not true for the square Plaquemine model, basically for the following reason, that if you've got a small droplet and there's some available entropy, you can always make transitions between those states that are making up that entropy. But it might require the very slow mechanism to do that. It might require you to make moves that require this large energy cost. And in fact, that is the case for the square plaquette, that there are, for small droplets, pairs of states that are can only interchange by the very slow mechanism and not by the fast mechanism that dominates at high temperatures and for large systems. So the final point I was going to make, I suppose, yes, oh, well, let's make it the final point anyway, is that this idea that I've illustrated rather sketchily here, you could apply just the same to the kinetic constraint model. So instead of having a hard constraint, you could have a constraint which is violated with some small rate epsilon. And then, because the thermodynamics of the kinetic constraint model are so trivial, all droplets eventually equilibrate. But the time for them to equilibrate would depend on epsilon. So then you could take epsilon to 0, and the time to equilibrate the droplet could blow up for some droplets. And you would have some distinction in that case between the dynamic and the static point to set, which I think is what we were discussing this morning briefly, that you may require big droplets to converge the equilibrium relaxation time, even though you've already converged the entropy. Yes. Okay, I don't feel that was very clear. Let's see if I can persuade you of 2 things, maybe. So you start with these simple models, and you introduce these kinetic constraints, which look a bit a priori strange. You don't see a particular reason why you should do that. But when you do it, you find that the relaxation times start getting big at low temperatures. You find dynamic correlation lengths starting to grow. You find big chi-4, dynamical heterogeneity, intermittent particle motion, all that kind of thing starts to appear. All this happens without anything funny happening to the entropy. So there's no obvious, well, there's certainly no TK in the model. There's no entropy crisis at which the entropy is going away. And there's no elasticity. There's lots of things that we've thrown away, and yet we still are able to recover quite a lot of this sort of glassy phenomenology. And I've also, I think I've failed to convince you of this. So I can only encourage you to, if you want to worry about it, find another source to illustrate and establish ideas. I think it's really true. I think that, suppose you have a new idea about glass, like we should measure the 4-point susceptibility. I think it's a good idea to go away and do it in a kinetic constraint model because it's easy to do with a computer simulation. You'll be able to understand the results. You'll be able to make a picture that illustrates the results. And even if the mechanism turns out to be completely different, the physics turns out to be different in the model you were originally interested, you'll learn something about what your method was telling you. And I think it's the same story with mode coupling theory, that we learned something about what's going into that theory when we started, well, not we, when people started applying it to these simple models. So the questions that I think are outstanding, which I'll come back to when everyone's had a cup of coffee, are whether these models have anything to do with glasses, first of all, and secondly, and perhaps more ambitiously, can you take a specific model and think about it as being related to a specific kinetically constrained model? Or is that perhaps a step too far? Okay, I'm a bit early, I realize. In England, my lectures are usually an hour. I think everyone is tired. So I propose to answer questions. And can we have some lights back? Do you want a mic? Or just shout?
So what are the key features in the constraints you would identify between those constraints which leads to Arrhenius and non-Arrhenius behavior?
Okay, so that's a good question. So what's important in the constraints to tell you whether it becomes strong or fragile in that language? So the usual story is that if you can find a way to make a diffusive mechanism in your model, then you end up with strong behavior. Now, of course, you can get strong behavior just by having any old activated rate. But in these systems, if you've got kind of diffusion plus activation, that's what will give you the Arrhenius scaling. Whereas if you've got an energy barrier that really gets big before something can happen, if you've really got, I mean, the naive picture, it doesn't necessarily help, is the idea of sort of a washboard potential. So diffusion in a washboard potential with a single energy barrier already gives you strong activated scaling, whereas diffusion in some kind of hierarchical landscape, whatever you like, would give you a much more super Arrhenius fragile scaling. So you have a few large energy barriers. Perhaps I should draw it the other way out, but because these don't look like energy barriers. But if you have a few large energy barriers and a lot of small ones, for whatever reason, that would be what tends to give you the fragile behavior. Any more for any more?
I was a bit confused at the beginning when you were talking, before you introduced the energy scale to make the constraints soft, you were talking about temperature? Or did I miss something?
Yes, right, I was, you're right. So just start with the trivial model. So just start with a model where spins just flip up and down with rates c and 1 minus c. So this is trivial. All spins are independent. But you can still, so you can associate the system with an energy function, which is just the sum over all spins of whether they're up or not. So you say a configuration with n up spins has energy n. And then the steady state is a Boltzmann distribution with that energy function and some temperature. So the temperature just becomes a way of parameterizing the steady state. I mean, it's a one-parameter family of models with either C or the temperature as the parameter. Is that?
Yeah, but so you're still using the hard constraints for the dynamics.
So I still have hard constraints
Okay.
here. Yes. I mean,
Okay.
yes, that's
Yeah,
right.
I just missed that.
That's fine.
Thanks. I get one more question. If you, is there anything interesting you can do by relaxing the detailed balance condition you had, and instead letting both, making all states go back and all transitions go back and forth, but not having the probabilities be equal? Is that?
Well, so the reason people like detailed balance is that it ensures that your steady state is time reversal symmetric, and equilibrium states are usually time reversal symmetric. So I think it's clear that if you start doing complicated things, then lots of complicated things can happen. So I mean, there's something simple you can do. You can just make all particles more likely to go to the right than to the left, and start trying to force a large-scale current through the system. And that doesn't obey detailed balance anymore. And the point is it becomes much harder to do anything analytically. The phenomenology becomes complicated, I would say. And it's not clear what it would be a model for in that situation. But you could certainly do it. And people have looked at it as a model for sedimentation, for example. So, yeah, put some gravity. I guess then you would have detailed balance, actually. But even then, if you do sedimentation out of equilibrium, you could think about doing that.
So I was thinking about the fact that all the three lengths are equal for the triangular plaquette model. But maybe, I mean, something that would be different would be actually the behavior, well, not in the triangular plaquette model, but it's in a real system which could be described by kinetically constrained model. If you look to the behavior of the time as a function of R, meaning that at low temperature in the random first order, you really relax fast because, well, you are blocked in one state. Instead, I would say that in the case of kinetically constrained model, in principle, while you have since there is a configurational entropy which is of order KB, well, I would say that you can still explore many configuration, and the small scale you don't have anymore the let's say the defect that make you relax, but you will use, well, you violate the constraint at the end, and so the time scale will be larger. But
so I think for the triangular plaquette and with the frozen boundary, it's not true that you have kV per particle of entropy anymore.
No, I agree. For the triangular, I agree. But you know that, I mean, if you use let's say a kinetically constrained model, then it has a problem because the configurational entropy is not of order KB like in real system. So to save the thing, you have to say that actually a spin which is 1 of 0 contains many degrees of freedom, which just can flip when the particle goes by. So actually, this is a kind of trivial configuration that you can reshuffle in the dynamics. But you will reshuffle, but on a time scale which will be very long. So because the time scale to violate the constraint.
Good, I agree. So
no, just to say that maybe is even in a case where the length looks the same, maybe the way in which they behave as a function of R and how they are with respect to the infinite on the bulk behavior, it's interesting to discriminate.
Yes, and I think there are other ways to discriminate as well, to do with whether it melts all in one lump or whether it melts gradually. I suspect that this condition that you have where the width of the transition goes down as something to the d over 2, I suspect that's not true for the triangular plaquettes and things as well. So
yeah, but maybe even for the mosaic.
Well, maybe the mosaic is what the triangular plaquette is, but I mean, it's a bit hard to know. All right, it's obviously on the next slide. So just to remind you, among a bunch of kinetically constrained models, the probabilities of different configurations, they're always equal. The configurational distribution is always equal. But the surprising thing happens when you ask about the probability of a trajectory or a typical trajectory and what it looks like. So what we're going to do is think about the idea of a purely dynamic glass transition, and we'll contrast that with a sort of traditional thermodynamic phase transition. So a classic thermodynamic phase transition will be freezing of the liquid to a crystal, and it shares these features with the glass transition, which is that you start with a liquid, you end up with a solid that seems rigid on everyday timescales, and you can, I don't know, make houses out of it or whatever you want to do. But what happens when the liquid turns into the crystal is that the probabilities of different packings really change in a qualitative way when you go from the liquid to the crystal. And you can compare that with going from a liquid to a glass, where the probabilities of the configurations change a bit, but basically you can think about the packing of the glass being certainly qualitatively the same as that of the liquid. There are some details. I think I can safely say that in this audience. No one's going to have a go at me too much. But definitely the properties of the trajectories change a lot as you go through the glass transition. So the particles go from being not moving to being moving. And that's a big change. So the idea, I guess, is that we should focus on the big changes and not worry too much about the details, let's say. So the motivation is, wherever possible, we'll ignore anything based on the configuration, like the entropy, like the packing, like G of R, and we'll just focus on dynamics, so relaxation time and heterogeneity, let's say, and those kinds of quantities. And we'll call them interesting, just to have a word for them, but dynamical maybe would be fairer. So here's a sort of picture which you might use to motivate kinetically constrained models as models for the glass transition. So this is not a model now in the sense of a lattice model. This is a two-dimensional mixture of particles with repulsive interactions going by molecular dynamics. And I've done the same thing that I did with a kinetically constrained model. Someone, well, neither of these people did the simulations, but Garahan and Chandler published these pictures. And the idea is the same, that the black particles or the gray particles have moved, relatively speaking, a long way, and the white ones have hardly moved at all. And these are three successive snapshots of the mobility field as time goes from left to right in this two-dimensional mixture. There's a lot of particles here. There's probably, I forget, 10,000 particles, probably more. And what you can see is that motion's happened here, and it's happened here, and it's happened here, but nothing's happened here. And then as you go from left to right, there's a sort of blob that grows up around this particle, and it gets bigger and expands to fill a sort of region, whereas you have regions where nothing's happened all the time that kind of stay constant for a while, and then eventually everybody's moved. And this is supposed to remind you of these four snapshots that I showed of the kinetically constrained model. And I think the phenomenology is very similar. And the idea of facilitation, so this word facilitation, basically it just means stuff happens where stuff's been happening. So if there's motion going on over here, it's likely there'll be some more motion over here. It's more likely there'll be more over here than it will suddenly decorrelate over there and everywhere else. And in particular, these blobs, these black blobs, they spread out as time passes. Okay. So this is maybe just too philosophical for this time of day. So kinetically constrained models obviously have this property of facilitation. Where motion's been, that's where motion's likely to be in the future. But if we're going to take a kinetically constrained model seriously as a model for the glass transition, for the liquid, we're somehow assuming that's the dominant effect, because that's really the only physics we've put in. We've put in that there's a kind of distorted packing, and we've put in facilitation and nothing else. So here's a hopeful analogy that you might not find interesting. So we know that generically, if you have a fluid of particles and it's dilute and they're attracting each other, then it's likely that it's going to condense into a liquid or possibly a crystal. And there's something universal about that physics in the sense that you just have particles, they interact each other, they condense. That's all you need. So in making the jump from, so this is a picture and this is another picture and they look a bit the same. But we really want to say more than that. We really want to say something about, something in detail, that they contain important features of the different models. So everybody agrees now, or many people agree now, that facilitation exists. That these pictures exist, and that this spreading out is kind of, it happens. But the question is whether it's dominant in some effect, whether it's sufficient to put that into your model and see glassy behavior already immediately, or whether one needs to put in a lot more physics of, I don't know what, packing. And here's a kind of grand hypothesis for this time of day, which is that the interesting features can be explained in terms of KCM. I don't know. I'm not seriously stating this, but it's an idea that one might explore. So we want to think in terms of making a mapping from a liquid to a kinetically constrained model. And it's not at all obvious that you should be able to do that. And it's, by the way, it's also not obvious that there should be a mapping to a spin glass either. I mean, none of these mappings are obvious a priori. That you change the degrees of freedom completely and lots of strange things are happening. So let's just think a little bit how you might do that. So here's these two particles in a matchbox that I showed before, and this example of reducibility. And I'm just going to model the particles around them by a sort of blue cage. And I'm saying that in this region, these guys can't pass each other, certainly without moving a lot of other particles. So that's really in the spirit of point to set. The light blue environment does a good job of freezing these two particles in their position. And that's typically what it looks like in the middle of a glass of hardish particles, I'm claiming. But in a few places, there'll be some loose cages. There'll be some places where the packing is a bit less dense and where the particles can now pass each other. So this we could call jammed, and this we could call mobile, at least on this sort of freeze the boundaries, think about the bulk way. And then you could think about trying to identify these sites, these mobile regions of the glass, and putting the glass on a lattice or the liquid on a lattice. And where you see something like this, you would put a 1, and everywhere else you would put a 0. And then you'd watch the dynamics of the glass, of the liquid evolve with the molecular dynamics, and you'd follow the 1s and 0s around. And then you would try and cook up a kinetically constrained model that would have the same behavior for the 1s and 0s, if you like. And it's not at all obvious that that's possible, but that was, to my mind, what Garahan and Chandler were thinking about when they started thinking about a dynamical facilitation theory in a serious way. And I just state as a caveat that the neglect of elasticity might well be important here, because if this guy's mobile over here and some motion happens, then all the elastic stress field allows that information about that process to propagate all through the system. And that's obviously something we've thrown away if we go to a lattice with purely local moves. So a lattice kind of insists that facilitation is a very strong effect because particles are only affected by their locality when you're working on a lattice. There's none of this long-range elastic correlations going on. Yes. I'm not sure that in reality 0 plus 0 can be 1. But in reality, many jammed regions can conspire together to become mobile. Absolutely. So it's obviously a very hand-wavy picture. And the question is, can one make any progress with it? So to do that, I think we have to take a step backwards. So you think, okay, so I've coarse-grained my system, and I now have these 1s and 0s as degrees of freedom that are floating around according to some local rules, let's say. But then what I want to calculate is properties of particles. I don't want to calculate properties of 1s and 0s. What do they have to do with the things that I'm used to measuring? So we're going to do something a bit strange, which is we're going to imagine integrating out all the particles and ending up with a theory of 1s and 0s, and then putting one particle back in again. So we have these Ni variables, and they're fluctuating around according to kinetic constraints and rules. And then we want to consider the motion of just one particle in the system. So we'll suppose that the Ni have their rules, which could just be the FA model rules, let's say, which would be, so 1 goes to 0 with rate 1 minus c, 0 goes to 1 with rate c, if, so this is site I has greater than or equal to 1 up neighbor. So both of these transitions, or either of these transitions, both of these transitions can take place if this is true, and neither of them can take place otherwise. And these would be the rates. And then I say I'm going to have a particle. So I don't have any particles yet. I just have these mobility variables, Ni. So now I'm going to have one particle, and I'm going to say he lives on a site. He lives on the sites of the lattice. And he can move only between adjacent upsites. Sorry, I'll stop writing here in a minute. Adjacent sites with ni equals 1. So if I have some state which looks like 0, 1, 1, 0, 0, 0, then if the particle is here, he can't move. But if the particle is here, he could move to here. So those are well-defined local rules for seeing how the particle moves around. And here is a space-time cartoon of what happened when one carries out those rules stochastically in time. So space is going this way, time is going this way. This is at a high temperature, so there are very many gray sites. And I've just plotted the trajectory of a particle evolving according to the particle rules. And basically it's diffusing here. And it's diffusing with a diffusion constant of order 1 because there's a high probability that there'll be a pair of adjacent 1s. And so it just diffuses like a free particle. And this would be a model, kind of trivial model for a high temperature fluid in this picture. And then you lower the temperature and you see that you get these large regions of zeros where, because nobody is up, nobody can move. And so you have these large immobile regions, and the particle tends to get stuck there. So the particle didn't move for a long time, and then it met some excitations, and it moved for a bit, and then it got stuck in another bubble, and then it's moved, and so on. So when the density of gray sites is high, the particle motion becomes intermittent. It takes place by these long quiescent periods, and then rapid jumps. And if you've watched a picture of a colloidal particle moving in a suspension, you see similar kind of behavior, that it tends to rattle around one position for a while, then it makes a jump, and then it rattles, and then it makes a jump, and then it rattles. So there's not really much gone in here. I've just made some local rules for the ends, and then I've put a particle in, and I've recovered this kind of correlated motion, which maybe you think is not to achieve anything, but again, it's an example of how this fairly rich phenomenology can come out of simple rules. So what more can we do? So in supercooled liquids, one often fits the self-intermediate scattering function by a stretched exponential with some amplitude q, at least for large times. So I'm always imagining I'm thinking about longish times because I don't have any elasticity. So let's think about how that might come about in a KCM. So you have a one-spin facilitated FA model, just the same one, just to have a model. Excitation density C, and the diffusion constant for excitations, I said before, is D proportional to C. So these guys are diffusing around, and I know the diffusion constant. And then I say, well, let's suppose that I have a particle now, so a particle in this sense, and he starts, let's say here, a distance L from the nearest excitation. So he's obviously not going to move until an excitation visits him, because he needs upsites in order to move. And the typical time for that to happen is the square of the distance divided by the diffusion constant. That's how long it takes, typically, for you to be visited by a guy L away. You have to be careful with your averages, obviously, here, but typical should be okay. It typically moves here, right? So do we like this? So then what's the fraction of particles that are a distance L greater than x from the nearest excitation? It just follows this exponential law because the excitations are distributed at random throughout the system. So particles that are close to excitations move quickly. Particles that are far away from excitations that then move slowly, or don't move for a long time. And there's this distribution of distances always, naturally, because I've got to be some distance away. And one can go through this. Okay, so if you just assume that a guy moves for the first time at time L squared over D, which is obviously wrong, there's obviously a distribution. But if you just assume that, then you should just say that the fraction that haven't moved at all at time t scales in this way. You just set x to be L here. And you get a stretched function for the persistence with beta is a half. And it's natural to connect the persistence function with the self-intermediate scattering of the particle just because the self-intermediate scattering function decays when the particle starts to move. And so the persistence function just reduces at, so this function, the self-intermediate scattering function, reduces at zeroth order just to the persistence function. And then there can be more complicated things, but that'll do for a start. So, do we believe this argument? Well, yeah, I think I believe this argument. So the persistence function it looks like a stretched exponential. You can do all this properly. It was done by Cristina Toninelli, and you get this result with probably some different prefactor here. But the stretching is robust, and the origin of the stretching is what I've explained. that you could be any distance from an excitation when you start, and if you're far away, things will relax slowly, and that gives you the long time tail in the stretched exponential. That gives you the slow relaxation times that contribute to the stretching. And I don't know if I put it on the next slide. Yes, I did. Okay, so this is what I said here, is that you can do it more carefully, and you find the same form with the same stretching exponent but a different prefactor. It can be proven that this is not a long time limit. This is not valid asymptotically at long times, and that the behavior crosses over to an exponential, but it's really a detail. It's not important for these purposes. In higher dimension, the stretching goes away for the FA model with f equals 1, but there are other models where the stretching is robust. And other KCMs, you can get various beta. You can get beta, the stretching exponent that depends on temperature. It can vanish at low temperatures. All kinds of things can happen. But the generic thing is that you always have, in a system that's kind of black and white like this, you have a distribution of environments. He could be in the middle of a bubble, or he could be in the middle of a gray bit. And that distribution of environments naturally gives you the stretched exponential behavior that you want. And so, why am I going on about this? I suppose I'm going on about this because people sometimes put it forward stretching as a kind of deep and complicated and difficult thing to explain. But just naturally heterogeneity, distribution of relaxation times is good enough. Okay, so stretching we can get arguments for in our KCMs. So what's another thing that people have considered a lot recently in the context of supercooled liquids? It's the breakdown of the Stokes-Einstein relation, which says that in simple liquids at high temperatures, the relaxation time, the viscosity and the relaxation time are proportional to each other and proportional to the inverse diffusion constant of the particles in the liquid. So, well, I don't have to repeat for you the Einstein and Stokes arguments, I guess. I'm sure that somebody would have spoken about it. And it's observed to, well, Ludovic Berthier spoke about it. And it's observed to break down in the supercooled regime. And a bunch of explanations for this have been put forward. But what they all boil down to, basically, is that there's a range of relaxation times tau. So particles close to excitation, in the KCM picture, particles close to excitations relax quickly, particles far from excitations relax slowly, and therefore you don't know what tau you should put here. So eta, the viscosity, is proportional to some tau, some relaxation time, and the inverse diffusion constant is proportional to some relaxation time. But if there's a range of relaxation times, you can't get all the way from eta to dp. That's the kind of loose argument. And so can we test this idea in kinetic history models? Can we really show that it's true or false or whatever? So the nice thing is that there's a lattice here. So I know when particles are moving. Particles really move in discrete jumps. And so it's very natural to think about a jump model or a continuous time random walk, which, again, Ludovic Berthier spoke about. So I'll just be brief. I guess the thing to say at the outset is these continuous time random walks are more general than any facilitation picture, but they do turn out to be useful when discussing models within the facilitation picture. So this is just to repeat really what you already heard. So you have particles on a lattice moving by unbiased hops. So have this particle, it hops around and therefore executes diffusion, but when it hops is randomly distributed. So sometimes it has to wait a long time before it hops, sometimes it only waits a short time. And there's some probability distribution of times, which we're going to call psi of t. And then there's just, so whether you think this is surprising or not is kind of in the eye of the beholder. But you can define two quantities, the average time between successive hops and the average time before the next hop takes place, starting at some random time in the system. And both of these are kind of loosely the average time to make a hop. And yet, they can be completely different. So if psi of t is the right kind of function, one of these can be infinite and the other one can be 1. I mean, there's really nothing that relates these things a priori. And you can more or less easily show that the exchange time is the first moment of this distribution, and the persistence time is proportional to the second moment. And what that means really is that the persistence time notices the long times. So the persistence time really notices this guy, who didn't hop for ages. He contributes quite a lot to the persistence function, but he doesn't contribute much to the average hop length, because this is just one hop among many. But there are a bunch of particles in here. So, right. So the persistence time notices the tails of the distribution of time, so the long times. And it's the same for the stretched exponential, actually. The fact that some guys take longer than average to move is what gives rise to the stretched exponential. So far I didn't really say very much. So within continuous time random walk, so within this assumption of independent hops, independent in direction, the particle diffusion constant comes out to be proportional to the inverse exchange time, but the structural relaxation time comes out to be of the order of the persistence time. And these are just different moments of psi of t again. So if particles follow continuous time random walk, we expect this ratio, which is something that's been measured in supercooled liquids, to be proportional to this ratio of persistence to exchange, which is 1 or greater. So I don't have data for kinetically constrained models, but I can tell you the answer. So the answer is this is good for the one-spin facilitated FA model in one dimension. That's this model. It's actually bad for most of the other models because if I can hop, I can very often hop back, but it's unlikely I can make another hop on. So you get correlations between the directions of hops. So if you try this with the TLG or the yeast model, it doesn't work too well, but it works well for the one-spin facilitated FA. And the good thing about the kinetically constrained models, again, is that they're on a lattice. So these tau x and tau p's are unambiguously defined and easy to analyze. So what about real liquids? So here's some data for real liquids. This is all quite busy, so I guess I should talk you through it. So it's a two-dimensional mixture of repulsive particles, he said. I think it's two-dimensional. It's a WTA mixture anyway. It's repulsive particles. And this top figure shows the ratio of the persistence and the exchange time. So we're not on a lattice anymore, so it's not obvious quite how to define that. But you define it by saying once they've moved a certain distance, that's judged to be a hop. And you can see that as you decrease the temperature, there's this strong increase in the ratio of persistence to exchange that starts to take off at about the onset temperature and gets actually pretty big for this model. Okay, so this is the ratio of persistence to exchange. And then this is the ratio of, or the product of the diffusion constant and the alpha relaxation time. This is just killing the units off. And you can see that, so there's two kinds of particles, it's a mixture. But you can see that the shapes of the curves look pretty good. The points at which they take off look pretty good. I don't know what happens if you take this data and try and put it exactly on top of that data. It doesn't, it's not the same. But it's pretty good agreement. So this is data. You can have issues with the data, but it looks reasonable. And so what's the role of facilitation here? Well, not much directly. Facilitation says that if you've got these excitations in the system and they're sparse, then you'll naturally have a broad distribution of relaxation times contributing to your hopping. So that means that psi of t will be broad. And that means that tau p over tau x is large, and that further means that d tau alpha is large. So there's a question when you look at this data of necessity and sufficiency. So how much do you need to invoke to explain this data? Just really a broad distribution of psi of t. But if you think about KCMs, it's apparent where that broad distribution is coming from, and that's not, it doesn't have to be the same mechanism in the real glass. But so that was all one particle quantities, right? So stretched exponential relaxation, that's a one particle quantity in the self-intermediate scattering function. Diffusion constant is a one particle quantity. Relaxation time is a one particle quantity, even if viscosity is not. And exchange and persistence times are all one particle quantities. So we need to think about collective behavior, because just explaining one particle properties is not going to get us very far. So this is just a picture, really. But they're quite nice pictures. So I'm sure someone will have talked about the dynamical propensity. So this is a way of visualizing where the mobility and immobility tends to be in systems, in particle systems. And it at least removes some of the fluctuation. So when one shows, sorry to go backwards and forwards, but when one shows a picture like this, it's really hard to do much with it because they're just pictures, they're sort of black and white, it's just one trajectory. You could have been lucky, it could be different. So one thing that you can do is take a structure, take an initial structure from the system and run lots of dynamical runs from the same structure and look at what happens on average to each particle. and you color red the ones that typically move a lot, and you color blue the ones that typically don't move much. And you kind of eyeball them, and you make a comparison. And the first thing to notice is they look kind of the same. They have this patchy structure with these large immobile regions and these more localized active ones. You can think about measuring correlation lengths for these things, which have all been done, and measuring how the time evolution of the specific functions goes. And all I really want to say is that the phenomenology is similar, but first of all, the phenomenology depends on the model that you use. So if you use, this is the TLG model, and if you use the KA22 model, you'll see something else. And if you do the FA33 model, you'll see yet something else, right? So I don't want to try to fit this data to this data, because that would just be fitting one model to one model, and I have no reason particularly to suppose that I should be using this one as opposed to any other one. But always the phenomenology looks the same. Always you have a peak in chi4. Often you have stretching. Always you have clustering. So really the question is, given that we have these hand-wavy methods of thinking about, so we have this kind of idealized coarse-graining cartoon, but we don't really have a way to make it more rigorous at this stage, really, which it's still at the level of phenomenology. Oh yeah, one more thing, just for fun. So often one fits data for relaxation times to this well-known Vogel-Fulcher form. And you don't get that in kinetically constrained models except for a very few rather specialized ones. So more often in kinetically constrained models, you get something like this. So perhaps we should, given that people always use this one, perhaps one should ask, what happens if you use this one instead to try and fit your data? So this is what the Elmatad in Berkeley did as part of her PhD, was she collected data for, I don't know how many liquids this is, and here's the raw data on an angel plot with log tau against Tg over T. And they say, okay, so let's try and fit it to this model, which is basically ends up being a 3-parameter fit. You have a prefactor and 2 constants, and this one is the same. It's a prefactor and 2 constants. So can you collapse it? The answer is, you can collapse it beautifully. So you shouldn't, just because people use this Vogel-Fulcher all the time, you shouldn't assume that it's the only thing that you could use. You can't say, because my theory is not consistent with this fitting function, it's not consistent with the data. Because clearly this data, I mean, you can get this for the East model. I'm not saying that the real liquid is described by the East model, but I'm just saying, beware when you're fitting these sort of smoothly curving functions over not very many decades. So you can play games and try and guess what all these things might be.
I don't remember now, but there were some quantities that shouldn't be negative, and so on. Say a little bit more.
So A is not guaranteed positive. My feeling is that's okay. So if you try and fit this one, you have a prefactor here. And the prefactor should be of order of the microscopic time. And often when you fit it, it's not. So maybe the Danish guys can tell us about the prefactor, because they've thought about it a lot. But so you demand that the prefactor should be of order, picoseconds or something for a liquid. We don't particularly have a constraint on the sign of A, and I think very often it's negative. But since it doesn't necessarily have a direct physical interpretation, I'm not too worried. B obviously has to be positive, otherwise it doesn't go the right way. So the short answer is, if you think A should be positive, there might be a problem, but I don't think A has to be positive. But what energy scale? Yes, that's true. Well, that's true. That's true. So you, right? So my recollection is, and it's not my work. My recollection is that this J is, I can't remember. So J and T0, right? So J is supposed to be the kind of typical energy to make something happen. And then T0 is some temperature scale at which the dynamics starts to be more cooperative, I think. And at that level, I think that the parameters have sensible physics behind them. So I would say that what is in this exponential should be an energy barrier over KT. But I don't see why the individual terms should be separate energy barriers. But I agree that the energy barrier should be positive overall. The thing in the exponential should be positive overall. Yes?
One question about the long times, the lower temperatures. I'm really worried that the agreement is good. Because, there was some argument that, in fact, there is a departure, or at least as far as I can correct, David Chandler expected a departure.
Yes.
Can we see it somewhere, or is it to be seen, or is it projected?
So I think that this is so the data is fragile liquids. And the crossover is what they call a fragile to strong crossover, and it's been seen in sort of supercooled water or something.
Yes, but the idea was that it would always be the case that this crossover happened, or am I wrong? I don't.
I'm hesitant to tell you exactly what other people think.
Because in my view, you're back to square one, because if you invoke this t squared, then you're not Arrhenius, then you have a diverging length. You cannot have a kinetic constraint in real life, so you have to invoke a correlation length that diverges, and you're back to square one with the only difference, which is not fundamental, that this happens at t equals 0, but that's not important. You're non-Arrhenius, so there has to be some cooperativity. So in order to really make a punch with the argument, you have to say, well, no, it becomes Arrhenius, which is, as far as I can tell, what David does. But I don't see it there.
So I don't think it has to cross over to Arrhenius if the energy barrier to violate the constraint is, well, I suppose it does eventually have to become Arrhenius, but it could happen at a very, very low temperature. I mean, the energy to push two Lennard-Jones particles through each other is pretty enormous.
Uh-huh.
And if that's what you're thinking of to break the constraint, it could be way up there. That's the first thing to say. The second thing to say is this is not all collapsing at TG anymore. So you're not sure quite where TG is on this scale for the different liquids. I'm not sure where it is.
No, but the time I can see.
That's true. But do you know what 2 is?
No.
Me neither. But it's the prefactor here. So there's some fitting in it. But I think they're all reasonable.
It's 16 orders of magnitude, so
Yeah, so it's...
saying 16 is where you'd be looking at.
I'm not I think the TGs are in... So these are collapsing at TG here. And there's not data for all of them up here. So TG must be here somewhere. For the different ones, there's some spread in TG. Sorry, I was trying to answer a question and I've now forgotten what I was going to say. Right, okay. My feeling about this is that people sometimes might say, if your KCMs don't look like Vogel-Fulcher, that's a reason to reject them. I think that this addresses that problem. It doesn't address the problem of diverging length scales at low temperature. And in fact, even the FA model, the simplest FA model with Arrhenius scaling has a diverging length scale at 0 temperature. It's just not big enough, not associated with a diverging energy barrier. So yes, I don't think there's a lot of new physics in this plot. Mostly I would say it's just a warning about what fitting functions you can learn.
No, the fact that it's sometimes presented as not what you were saying, but just as evidence that you do not need a diverging correlation.
Now, you are either going to invoke Arrhenius anywhere, you could have done it also at the level of Vogel-Fulcher when you did it, or if you're not invoking Arrhenius, this implies a divergent correlation
Yes,
length.
I agree. And I think that's implied in most of the models as well. Okay. So I thought that might cause some debate. That's why I put it up, really. So what can we conclude from what we did? Well, I'm claiming that these KCMs, which have simple thermodynamic properties, no entropy crisis at finite temperature, anything like that, can still be glassy. So you can still kind of put the data alongside the liquid, and it's hard to tell which is which. So apparently there's some quote from Hans Andersen that if it looks like a glass and quacks like a glass, then it may as well be a glass. So I don't know. That's the first thing I'm claiming. I think that's reasonable. And the second thing is that we can get a long way without asking particularly about structure. So there's not really any structure going into any of this. I'm not telling you anything about what packing is associated with ni equals 0 or 1. I'm trying to make arguments that are more general than the details of the packing, and ask about dynamics only. So I think that it's an interesting question to ask. Is it possible to turn this into a working theory of the glass transition? And what would that mean if so? And what would we require in general from any theory? For me to stand up and say, this is really a theory of the glass transition instead of this is some thoughts about the glass transition, what would I need? So the most exacting thing you could probably ask for is sort of machinery for analytic calculations based on, I don't know what you like, pair potentials. Or maybe you could think about a precise procedure for doing the coarse graining trick that I showed, a precise procedure of coming up with ni variables from liquid variables. Or you could think about some universal features that you find in KCMs and making a mapping at that level, at the level of sort of universality arguments. So I have some time. So I'm not going to say anything about machinery of this kind because I don't know anything. I'll say a little bit first about mapping liquids to KCMs. So I guess what I want to argue is that it's possible to see facilitation ever more clearly as one looks more and more closely at the data. And one can at least ask the questions now, what rules could I use to describe the motion excitations in these systems? So this is, it's better on my screen than it is on this screen actually. But this is some 1,000 ball bearings, I believe, vibrating in a vertical air current, and the density is quite high, but they're still jogging around, so they're feeling some stochastic forcing, but they're also crowded. And this says increasing mobility from blue to red. This is in a specific trajectory. So you see these strings, these red strings, that are where motion's been happening, and you see these blue regions where nothing's been happening for a while. So this is clearly a heterogeneous system. But what, in a way, one would like is to make some kind of plot. Sorry to go back. So we have in mind something like this, right, with space and time and lines. So can we do anything like that? Well, people have tried for the liquid. It's pretty hard. But for this ball bearing system, it seems to be more possible. So this probably doesn't really come out. But what these are is 2 plus 1, so 2 dimensions of space, and 1 dimension of time. And you can kind of see that there are blobs where particles have been moving, and you can kind of see, well, in this case, you can see these sort of avalanches moving upwards in time. And you can see that they're not connected together, but they have this sort of feel of little vacant bubbles with lines moving between them. So I would say that for a real system, these are the pictures that have been seen so far that are most like the excitation line picture that I showed before. And the main difference between these pictures and the one I showed before is the fact that you get that everything stops, nothing happens for a while, and then something happens again spontaneously. And this is increasing density here, so this is the highest density. So I said at the beginning that I think that people are now beginning to agree that facilitation does exist as a process. Or as an effect. And I think this is nice evidence, and this is just the same data plotted a different way, just collapsed onto the spatial degrees of freedom. Right. So that's just further evidence of what I said, really, that the facilitation exists and can be observed. So can one think about mapping this to a kinetically constrained model? I think it's hard. The main thing is that sometimes you observe motion starting far from any excitation, and you can get around that by softening the constraint. So you say, well, the constraint's not a hard constraint. Sometimes motion appears over here and then goes away again. But then, if you assume that, you'd naively expect the facilitation to be a stronger effect at low temperatures, and that scaling seems to be unclear yet. And also, it would be nice to associate these ni equals 1 with some structural feature of the packing, and no one's had much luck in that area just yet. But people are still looking at this kind of effect and what one can learn from it and how it scales. So do I want to say anything about this? Let me just say something quick about this, because it's something that we've been working on the last, well, quite a few years actually. And it's an idea about kind of universality. It's an idea about phase transitions in models and how that might relate to phase transitions in particle systems. So most kinetically constrained models remain at Gottingen temperatures, and so they don't have ideal glass transitions at finite temperatures. And so we had this, well, there was this idea, let's say, which is to find a phase transition in this dynamical sense. So these systems have interesting dynamics. So to find a phase transition in these systems, we should extend the methods of thermodynamics from space to space-time. So one should think about doing what we would normally do in thermodynamics to find a phase transition, but instead of dealing with the statistics of configurations, how probable a configuration is, one should deal with how probable a trajectory is. So if you remember, long ago, you thought about the microcanonical ensemble in statistical mechanics. You say, well, I'm going to fix the energy E of all my configurations, and then I'm going to ask how many configurations are there with that energy and what are those configurations like. And you find at high energy, they look like fluids, and at low energy, they look like crystals, and in between, there's a phase transition. So now let's do something else. We'll consider trajectories with a fixed value of the activity, that is the amount of motion in the trajectory. And let's just take that, for example, to be the number of accepted moves in a trajectory of length t obs. So I'm always proposing moves. Particles are trying to move, but very often that move is forbidden by the kinetic constraint. But whenever it's compatible with the kinetic constraint, whenever something happens, we'll add 1 to k, and we'll consider all those trajectories with a fixed value of k. Except we won't do that. I'm sorry. What we'll do is we'll go from the microcanonical ensemble to the equivalent canonical ensemble. So instead of using a fixed energy E, we use a fixed temperature in order to set the values of energy. We're going to do that the same here. We're going to use a biasing field. We're going to call it S, which is just like the temperature. So it fixes the average of k instead of k itself. But that stuff was fixed way back when they fixed thermodynamics. So we don't have to worry about it anymore. You can think about just considering trajectories with fixed k. So I'll be brief, because it's late. This is how we do thermodynamics. The partition function is the sum over all possible configurations of the system, e to the minus beta times their energy, or their enthalpy, maybe it should be. Because I'm thinking about being at constant pressure. So this is a partition function. Then I change the pressure by delta V. I know that the pressure is conjugate to the volume V. And so I have a new partition function which looks like this. This is standard from every textbook you've ever read. And then you can get the volume of the system by the derivative of the logarithm of the free energy with the minus sign, which is still missing here. There should be a minus here. But the specific volume you can get from a derivative of the free energy with respect to pressure. Well known. So now we're going to do the same with trajectories. So a trajectory is just what happens in a system over some observation time, t obs. So I can make the partition function to be just the sum over all trajectories of their probabilities. It's trivially equal to 1, because the sum of probabilities is always 1. But then I introduce my order parameter, my activity or my mobility k, which was the number of accepted moves in the trajectory. Then I can write down this generating function like object, which is directly analogous to this partition function. So this is, well, it's the partition function with an extra term, so it's like a generating function. And then I can get the mean activity as a function of the biasing field S, which has this form, which has the minus sign in it correctly now. So I said I was talking about phase transitions. So if I was doing thermodynamics and I found a phase transition, what would I find? Well, let's consider, for example, the transition from a gas to a liquid, from a vapor to a liquid. So I would increase the pressure, and I'd see a jump in the volume per particle as I increase the pressure. That's what I would observe if I was doing canonical NPT thermodynamics. And the width of the transition would be proportional to the system size. So it would be a real jump only for an infinite system. Otherwise, it would be a crossover with which 1 over n. And then if I work at P star, the coexistence pressure, and I measure a histogram of the volume, I would see 2 peaks like this, and I would interpret this peak as the vapor, and this peak as the liquid. And I would interpret the depth of this trough as something to do with the surface tension. So now I'm just going to do the same thing with my non-equilibrium trick. So I'm going to have the field S, the activity K, and I'm going to measure how K changes as I vary S. So I should say probably that there's something special about the point S equals 0, right? That's the point of physical dynamics. That's the point at which that's just the original ensemble of trajectories. So there's something special about the point S equals 0, which is up here. But what I'm going to show is that I see similar phenomenology at finite S to what I saw before at finite P star. So I'll have 2 peaks now, This one will be the high activity peak, so it will be the fluid, and this one will be the low activity peak, that will be the glass. So I was working on this, and we had our kinetically constrained models, and we knew that we could do things with kinetically constrained models, so we worked out what happened in this ensemble for those systems, and it's clear, I think, that the presence of any inactive configuration in the model gives you immediately a first order phase transition in this sense, and the transition occurs at s equals 0. So the model has no phase transitions when you just consider thermodynamics. But now in space-time, in d+1 dimensions, it does have a first order phase transition with some kind of peculiar critical point with a diverging length scale at 0 temperature. And you can do numerical results. This was done by a cloning procedure developed by Jorge Corchan and his co-workers. And you can get numerical evidence for the TLG model, for the yeast model, for the FA model, for any model that you choose. And so you've had this idea with these kinetically constrained models, so then you should go away and test it for a liquid and decide if it's just an artifact, because remember, these KCMs have these hard constraints which perhaps aren't realistic. So we need to generalize our activity K, but we just measure some measure of local mobility. Doesn't really matter what it is. We did some computer simulations. And here's the data. So this data is supposed to remind you of this figure. I think that's all I want to convince you of at 5+5 on a Friday afternoon, is that So what's happening here is the observation time is increasing. That's equivalent to increasing the system size for the thermodynamic calculation. There's a transition which looks like a jump in K, which is getting sharper. It occurs at finite S, and it's getting sharper, and it looks like it's going to turn into a jump at some stage, maybe. And then you can make the histogram. So the only thing that's not quite honest in the comparison I showed you is that before I wrote log P, and now I'm writing P. So this is not a log scale, this is a linear scale. But still, you can clearly see two peaks in the distribution of the activity K, which one might associate with a liquid phase and a glass phase. Oh, I didn't put a conclusion for this piece. So what does this mean? It means that if you generalize thermodynamics to one extra dimension of space plus time, then already in KCMs you see interesting behavior which you might or might not have expected. And further, that behavior does seem to generalize fairly well to a realistic particle model. And the idea is that there are configurations of the system, well, trajectories of the system at least, that look like a glass that you can achieve, that you can access, and are possible even when the system is at equilibrium at a fairly high temperature. So this temperature is above the onset, or at least below the onset, but well above the mode coupling transition. And yet, you can still see two well-defined peaks if you bias your dynamics in an appropriate way. And our idea is that this is maybe a way to establish a connection of the level of universal phase transition physics between kinetically constrained models and real glasses. And it's built on a bunch of old ideas to do with metastability in the spectrum of the master operator that was worked on a lot by Jorge and Julio and by mathematical physicists before that. But we think it's interesting and novel to start from KCMs and work towards doing sampling for liquids. So I think I've spent enough time. So what can we conclude from all of this? So again, facilitation is this idea that motion is clustered in space and in time. And it's observed in experiments. I don't believe there's any argument anymore that dynamical facilitation occurs. And the idea of it is encapsulated in these models. So you start with an idea about how reality is, you make a model that shares that feature, and then you say, well, does the KCM describe the world? Well, we can at least test the experiments that we want to do on real liquids on KCMs, and we can see the relationships between these non-trivial phenomena like heterogeneity, stretch relaxation, decoupling. That'll do, that's enough, isn't it? So we can test these relationships in model systems and compare back. So we have in principle, we have a closable loop between hypothesis, model, refine model, go back to experiment, test again, and go round. And I've tried to emphasize that the kind of arguments I've been using have been explained without reference to structural or thermodynamic ideas. So obviously if you want to answer structural and thermodynamic questions, you have to use the methods of structure and thermodynamics. But all I'm trying to say is that if you're interested in these kinds of questions, you can get a long way, not all the way, but a long way by just dealing with dynamical observables from the beginning and not worrying too much about where they come from. Okay, I think that's enough. Questions, everything.
I'm interested in your last comment, the last comment, because it's telling us that
It's telling us that maybe we don't really need to worry about having a phase transition, an ideal glass transition at all. And I guess if you came out of the old Ferry school of free volume, you would agree with that 100%. That, in fact, the glass transition is a purely kinetic phenomenon, and you don't really have to look for an ideal glass transition. And so in fact, that kind of argument might fit very well into that set of ideas without having to invoke that this is really a true first-order transition, but it's something that you're seeing. It mimics the glass or something, or it's a liquid behavior approaching the glass, sort of. But it's at least worth thinking about is that there is a school of thought that doesn't think that there's an ideal glass transition, and maybe you're actually providing evidence to support that school rather than having to dig around looking for an ideal glass transition where we can never reach anyway. You know, so maybe that's a comment and a thought. But the other question I have then, and maybe you can comment on this too, is if I have these dynamic heterogeneities, these structures that are mobility structures, if they're the cause of the slowing down as opposed to just reflecting the slowing down, or you know, the heterogeneity, then why do we see after a certain point time temperature superposition in the dynamics when this clearly this distribution of facilitated regions is changing really dramatically, I think, and yet the dynamics say, well, all that's happening is that the average relaxation time is shifting and everything else is staying the same shape.
Okay, that's two big questions, I would say. So the first question, I guess I didn't say, and I probably should have said, that the idea of constructing models based on facilitation does go back a long way. So you can think of, I don't know, defect models in Glarum and Montrol and people over a long time, and free volume theory, thinking in those terms, and I didn't mean to underestimate what that's all meant. You can argue about whether the facilitation picture is nothing more than that reinvented or whether it has new ingredients, and I believe it does have new ingredients, but I agree completely that one is very much in that spirit of those old arguments a lot of the time. Then the second thing that you said was
Time temperature superposition.
time temperature superposition, good. So in the models that we have, the scaling works, so you often get pretty good time temperature superposition, pretty good scaling laws. And I don't think there's any contradiction there because, so, I mean, I don't have a slide, but, okay, if you think about, this picture, there's no particular length scale in this picture. So even though the distribution of lengths is changing a lot as you change the temperature, it's changing in a sort of self-similar way. And so it's not unnatural to get time temperature superposition in that situation.
Okay, so in your case, you're seeing that they change in a self-similar way, so that might be not. But other people have reported changing distributions, right?
So the answer depends on the model, I would say.
Yeah.
So if you choose the right model, you can probably have anything you like.
Precisely when you fit only your liquid with the scaling of the different level, here you choose one particular model. This one particular model precisely does not apply the time as beta goes linear.
So I don't, I don't think, so, okay. I don't think that this figure means that you can map any liquid you like onto the East model. That is not my interpretation of this figure.
What does it mean then? I mean,
It means that you don't need to invoke finite temperature singularities to fit the data very well. And you can use other, I mean, you can use some other function here. I don't mind what function you use. I guess the main point is that I don't think you need a Vogel-Fulcher TK. That's so. Different people will claim different things about this figure, but I'm not going to argue. And even if you look in the paper, there's an argument that you can get the same physics from just a Gaussian distribution of energy barriers. You can get the same kind of Bessler form. So there are many ways to derive any kind of empirical law like this. Look at how many ways there are to derive Vogel-Fulcher.
don't try to say there is no underlying message beyond.
I'm only going to say what I'm prepared to defend. Yes. Any more? Is that?
That was. There is a whole family of kinetically constrained models, like the ones which are collective in behavior. And it seems that those ones are just useless for normal liquids because their behavior is very different. Do you have any intuition why just one of these models is more useful for describing the physics of supercooled liquids, to fit the data at least? Like why would
So which
the
ones
East model seems to be the preferred one now? Or so what about all the others in the family? The family is very large. Why just this one?
So I think if you want to do things at the level of collective behavior, you probably need to go beyond the East model, I would say. So this is some kind of cooperative model. And you can at least put these pictures next to each other. And you can put the chi-4s next to each other as well and see something that looks sort of in the same ballpark, I think. You're more expert than me, I would say. I think it's open, is the short answer. Yeah, that's what I think.
Yeah, I just missed one point. Please, may you go back where you talk about cloning of trajectories? And I just missed, which is the decision parameter that you have to clone or to kill trajectories? Yeah, that.
So it's what we call K.
Okay. Just activation, if they are activated or not. If the trajectories are activated?
Active. I mean, so when a spin flips, it counts 1 to K. And so then K is some extensive in time quantity, which we use in the cloning. So yeah, that's really true. So this is not, well, whatever. What's plotted is not quite what I said, but if I plot what you should plot, you see just the same. So yeah, it's just that.
And I just want, maybe it's a very basic question, but what is the aging behavior of these models? For example, is there any scaling in the correlation function? How is the FTT violated?
It's not a stupid question at all. It's been looked at least for the simple models, it's possible to get quite a long way. For the cooperative ones, somebody probably knows better than me in this audience. So for the simple models, there is good scaling. You can get different kinds of FTT violation, including negative response, which you may or may not think is very physical. For the cooperative ones, I refer the learned gentleman to somebody else, like Jorge. But yes, or Mauro Solito, who's not here.
So the aging is not very clear which model should.
I don't think you can resolve the questions that we haven't yet resolved by looking at the aging, because it has been looked at. I don't know if that helps.
So regarding this space-time phase transition, I don't know if I missed something basic, but so in the facilitation picture, is this necessary that you have this phase transition, or you can still have the overall facilitated dynamics but no phase transition when you look at it this way?
So it tends to. So from what we know, it seems.
So how should I understand the existence of this? Well, it's what. Yeah. So sorry. One other question is, I mean, yeah, how nice a phase transition is this? I mean, it looks at some superficial level like one, but I mean.
So for the kinetically constrained models,
yeah,
then what I wrote here is true. So there are sufficient conditions to see this phase diagram, which has a real first order jump in the classic sense from active to inactive behavior. Now, if you go back to Jorge and Julio's paper, it's pretty clear from there already that you can't have a transition at s equals 0 in a system without hard constraints. And so in a system with short-ranged forces and no constraints, you can't have this transition at s equals 0. But you could have a transition at small finite s, and that is in fact what we think happens. So that we have some sufficient conditions. It's also reasonably clear, I think, that in the 1RSB scenario, in the sort of, well, I don't know if I distinguish 1RSB from RFOT and everything like that, you can also get this kind of transition. So it's not necessary that you have facilitation to see this, because you can see it in other kinds of model as well.
I'm asking the other way. How intimately related to the ideas of kinetic facilitation is the existence of this transition?
So it seems to me that it's very generic in models that have the feature of facilitation, but it might be even more generic than that. So certainly you'll get a good crossover whenever you have long-lived metastable states in any model, whatever kind. You'll get a crossover of this sort, whether it's infinitely sharp, whether it's a singularity. That's up in the air. But this is generic to systems with long-lived metastable states, and that's. I mean, so then it becomes a question of how useful is it really to distinguish theories, but it's always useful for finding the metastable states in your system, even if it's only useful for that.
Well, any other questions? If not, let's thank Rob again.